All right, so, holy cow. Now that I've been enhanced, I'm going to apologize before I really get into this. I got no sleep last night. I don't know why. So I'm probably going to talk about furry hamsters that are dancing across my monitor because I'm seeing things right now. But I'll try to be as witty as I can and cover the material adequately. If I miss something, feel free to raise your hand and I'll try to address your concerns, hopefully without making an idiot of myself. So why am I doing this? Why high availability with Postgres and Pacemaker? And all the little things in between. I'm going to cover DRBD, CoroSync, LVM. There's so many different parts in here. It's a giant, giant stack of stuff. And it really is pretty involved. I had to spend weeks going over this myself just to make sure I didn't screw it up just for this presentation. Learning it was ridiculous. And I'm not going to exaggerate that you'll make a lot of mistakes in trying to set this up. And that's just the way it is. It's a big stack of stuff, and especially with Pacemaker. It's very, very finicky. But when you get it working, worth every dime. Well, it's free, so I guess you're not paying any dimes for it. But so, again, this is me. It's a really old picture. Ignore it. So what do I mean when I talk about high availability? It means the ability to stay online. In the context that I'm talking about here, I want my database to be up as much as possible, no downtime ever. And if it does go down, I want to be able to bring it back up instantly. I don't want to have to scramble to find some hardware in a cabinet somewhere. I don't want to have to spin up some nodes to wait for them to boot. I want it just to be back up again. Again, goes back into surrounding hardware failures. But the other thing you get with this is I don't want transaction loss. One of the things that Postgres gives you with its transaction log files, the xlog directory or replication and hot standbys, warm standbys, all the different ways they give you to protect your data, is it's really, really hard to lose it if it actually is written to disk like it's supposed to be. But there are exceptions, like when you lose an entire machine. And if you're exporting your transaction logs, do you really know they got to the other machine? Do you know your replication's working the way it's supposed to be? So there's lots of different ways you can do replication. There's probably more than the half dozen I'm going to talk about. But there's the basics, your trigger-based ones, Sloaney, Bucardo. You basically copy one table or even just some select statements across to another node. But you're not really copying everything, and it's only based on what the tool does. So you could lose something in there, especially on a highly transactional system where you're handling thousands, tens of thousands of transactions a second. Really good opportunity there to lose your data, not what you want. Multicasting, something you have with PG Pool, same problem. There's just an inexact data transfer there. It'll do your job. Great for reporting, great for spreading the load, making sharding, lots of different solutions there. But if you really want to make sure you don't lose any data, financial data, it's not quite up to the task. I know that someone here from Enova is going to disagree with me on that because they use it a lot, but I'm not going to get into that right now. I'm just trying to focus on my presentation here. And of course, we have log shipping. I mean, way back in the old days, 7.2, all the old stuff. That's how you got your data to a new server. You took the actual data files that were going to be applied to your data, to your actual data, send those somewhere else to be replayed. That's great. It's awesome. But transaction files that are in the middle of being written, if your machine goes down, gone. And you also have your polling interval. So, I mean, there's just a lot of opportunity for loss. Asynchronous is the same way. It asks for the data, master sends it. If you don't ask, you don't get it. And there's also no verification that the data actually made it safely over to the new node. Again, you could lose data. And again, it's not going to be available immediately when you want to flip a switch to become a full master again. Bah, we have 9.1, synchronous replication, the holy grail that we've been waiting for, what, a decade? So there's a couple of things that that isn't really heavily advertised about Postgres synchronous replication. It is synchronous. When you send the data file over, the transaction is safe, it doesn't get written to the master until it gets acknowledged by at least one slave. Great. But it doesn't get replayed on the slave either. The guarantee is only that it makes it to the slave, not that it's actually processed there. So you, again, have some opportunity for something to happen so that that data doesn't actually get replayed properly. The other problem you have is currently, this may not be the case in future versions, or you can find ways around this by restarting Postgres, but currently, the default with the master is if a slave dies, Postgres dies too. Well, it doesn't die, it just waits until it can get a slave to acknowledge the fact that it's writing the data. Because it wants to guarantee that that data is safe. And the only way to guarantee that data is safe is that it gets written to two places at once, right? So in order to get that, they won't let you write a transaction unless it's being written to at least two nodes. Pretty simple. But if you have a highly transactional system that's handling 10, 20,000 transactions a second, that will kill you. Even 1 second of lag, because your slave hiccups, there's a network hiccup, or the slave goes down and it's rebooting because you're doing some maintenance. You have to monitor and then restart Postgres with a new config setting that says, don't wait for the synchronous transaction for just a few minutes while we're rebooting and doing maintenance to the server or whatever. That's all stuff you have to manage manually. Currently, this is all new stuff, so we're finding new ways to work around it. But these are all little things you kind of have to think about when you're implementing these solutions. So there's a tool that's kind of been around for a while that solves some of these problems while introducing its own, but we'll take the caveats as they come and try to not get too far into it. So what DRBD is it stands for Distributed Replicating Block Device. What that is basically a network RAID 1. So a RAID 1 is a mirror. Data here, data here. Okay? And unlike the synchronous replication with Postgres, if node 1 dies, node 2 still has your data. It's going to run just like, and it's underneath the file system. So Postgres doesn't even see it happen. It just sees, oh, my block device is still there. The main difference here, though, is these block devices are going to be on different servers. Why on different servers? Well, one server dies, your data is still safe on the other. Now, how DRBD works is on the default setting, data is not synced. If you call an fsync to tell a disk to write the data, an fsync is not successful until it comes back from both systems. So this is on the block level. Every 8 kilobytes, or whatever your default is for your file system, it will not say that data is successfully written until it is successfully written to both systems. So what does this give you? Well, if data is written to node A, you can guarantee it's been written to node B. If node A dies, node B, if you're running as a hot master, you just got to restart it so that it's back in writable mode. If you're doing a warm standby, it's just like a recovery. Actually, no, I'm being an idiot. Okay, so it's not mounted. The file system is not mounted at this point because it can only be mounted on one, right? So it goes down. One of the jobs that Pacemaker does is it monitors it this whole time. And it says, okay, DRBD, it's time that node A died. I'm going to bring all this stuff up on node 2. So it mounts it, brings it back up, and starts it. This is the same thing of what would happen is if you restarted node A. All the same data is there. It's not doing you don't need recovery.conf. It's basically just starting a fresh node like it had just crashed. It's a little bit safer. And there you go. It's hidden from PG. PG doesn't even know it's happening. It's below the file system, so even the operating system doesn't even really know it's there. The other thing that it gives you is your synchronization is automatic. So remember I mentioned node A died, node 2 took over, node B took over. When node A comes back, even if you've been writing data to this one, it keeps a data map on both systems. So it knows which data has changed. So it'll actually resync all that data that's changed back over to the node when it reappears. This data could be all of the data. Say you reformatted the system, put a brand new system in because the other one was completely dead and it was on fire or something. The new node would start from scratch. The old node would catch up, but it does this automatically as soon as it connects. It kind of runs in a degraded mode, kind of like if you were in RAID 1. Your RAID 1 would say, I'm in degraded mode, don't really depend on this data until you get another disk in here. Well, it's the same thing. There's a status thing you can check that will actually say, well, I'm in degraded mode, don't really depend on me until you get your other node back up. So it's a pretty handy thing to have. But why Pacemaker? The really important stuff. You don't want to have to be there watching the nodes all the time. It's obvious that there's a lot of commands involved to remounting a file system. If you have LVM started, you've got to rescan all your file systems to make sure they show up. Then you've got to mount them. Then you've got to start Postgres. Then you've got to start all the independent services, like if you have a PG agent running or Sloaney or Bucaro. You've got to start all that up. No, it'll do it for you. And it's pretty fast. I think on my VM, and VMs are slow, right? About 10, 20 seconds is what you're going to wait for getting a system back up online. And this will probably come up. Why Pacemaker instead of something like Red Hat Cluster? Or there's another product out there called Lifekeeper from a company named Sios. It's a kind of a commercial entity that does similar thing like this. And there's really no reason. I like to think about it that Red Hat Cluster Manager is kind of centered more on the Red Hat, life cycle. So if you want to kind of separate yourself from that and actually have a more agnostic, tool, then Pacemaker is probably a little better for you. Yeah. Oh yeah. So I'm going to actually get into that when I get into the actual presentation. So I'm actually going to build a cluster for you live. I've got 2 VMs running on my system right now, and that's why I was kind of screwing around with my my nodes over here. This is node 2, this is node 1, and I've got a handy little cut and paste sheet over here for my commands. So how this will actually work is at the very end of this, we have a virtual IP, right? And the virtual IP will also be handled by Pacemaker, and it will point to the little active live node. Then when you just point to that, say I've got 192.168.56.30. .10 is node 1, .20 is node 2, and .30 is the cluster. Obviously, you don't have to use that naming scheme. I just threw this together for the presentation. But it kind of leaves you open to do a lot of different things. Another thing I like to point out while I'm actually got this with me is that DRBD and Pacemaker will generally, if you have some bigger iron hardware, will generally operate on their own 10 gig E, which is like an interface between 2 machines. That way you don't really step on other traffic going in and out of the machine, and all the synchronizations between the 2 machines are going to be fast as possible. Remember, this is block level traffic. You don't really want any kind of latency in here. Definitely wouldn't recommend it for an Amazon ABS. So this is an overview of what I'm going to be building. Just a basic 2-node cluster. I probably could have put this on Zen or some other VM. I'm putting it on VirtualBox. That's what I'm used to. It's really easy to set up. Maybe later I'll kind of pick up the more open source tools. Regular old Ubuntu 12.04 LTS. Why 12.04? Because it just came out. It's something people are going to be familiar with because it's Ubuntu, and it's a long-term stable, so theoretically it'll actually have some good support for the next few years. And the other reason is it's really recent, so a lot of the recent tools we want, recent versions of Pacemaker, recent versions of DRBD, recent versions of CoroSync, they're all in there. And they're all out of the box. I can just run a quick command, install them, they're there, and you can just use them. A few configuration files, you're done. What I did is I added another device to these VMs just for the Postgres stuff. I put it in there as SDB. So SDB is the regular, the OS and all the junk. And then SDB is the 500 meg partition just for Postgres for a PG bench partition. So that's going to be our external device. And the reason I did this way is because you're probably going to do that yourself. Whether it's like a SAN or a NAS or some kind of external device, or you're going to use if you have an NVRAM card like Fusion IO or RAM SAN, that's going to be two things you'll link between the machines that will be in the machines themselves. So you couldn't really use a shared RAID device that way. So it's not completely common, but something you'll probably run into if you live around enough. And then Postgres 9.1 straight from the Ubuntu repos. Again, I probably could have used the ones supplied from Postgres themselves, or did a compile install. For this purposes, just install from the repo. It's just all cut and paste. It works. I've done it plenty of times. And then DRBD and Pacemaker also from the repos. Again, because they're most recent well, they're not the most recent versions, but they're recent enough for our purposes. So there's a few things about DRBD and LVM. So DRBD is a handy-dandy little thing to have around, but LVM and DRBD are kind of kernel-level modules, so they don't really like each other all that much. So you've got to tell LVM to ignore DRBD. So one of the things you have to do on each of your nodes, the other thing is I'm going to be root on these because why not? Like 90% of the commands I'm going to run are roots, so. All right, so these lines here, where we've got filter, I'd like to point out that this line basically tells LVM what it should watch, like what it actually has domain over. And those R lines basically tell it to remove those objects. So remember how I said dev SDB is going to be dedicated to DRBD? I don't want LVM to manage that device because then it will conflict with DRBD and they won't know who really owns it. It'll cause a bunch of screw-ups, and it's just better to tell it to ignore it. The other things I told it to ignore, dev disk, dev block, those are because those are lots of aliases that could also point to a dev SDB. And that final one just says add everything else. And that's there because DRBD, there will be a device called dev DRBD0 that will appear and disappear pretty much at will. And we want LVM to catch that one because that's the one where the actual data is. The other major thing we're going to do is this write cache state. We're turning that off. The reason for that is, like I said again, the DRBD device will disappear and reappear based on which node the DRBD thinks is going to be live and active with the data. So we don't want LVM to cache that because it could be wrong at any point in time. We want to rescan it every time it actually wants to add the device. A few milliseconds of time, not really going to hurt anything. Not going to change your boot times. And that's on both nodes because we want, this is for machines level state. The other thing we have to do is after we make those two changes is when Linux boots, it actually boots off kind of a RAM drive that has a cache state of all the little bits and pieces so that it can actually get a hold of it before it boots the OS proper. Well, clearly the first time it booted, LVM stole all the devices it could because DRBD is not really a default service. So what ends up happening is these two things I just did are ignored until I reboot again. So, and also the rebooted state is cached. So I want it to regenerate that cache. And again, that goes on both nodes. So I'm going to go ahead and do that real quick. And while that's running, So when I say install tools here, I'm just basically, apt-get. If you're using Red Hat, use yum. Install. There's a package called drbd8 utils. And drbd is actually integrated into the kernel. It comes by default. It's in the kernel itself. It's going to be there, but the tools that actually manage it and control it are not. They're not a default thing. So if you want to actually say, okay, drbd, add this device, init this device, do this thing, you need to add the tools. I'm not actually going to have that command in there, but it is in my slides. So all the commands in here that I actually have for actually installing which services, those are all in there. I didn't know if I had a live network service, and I didn't know how long it would take to install this stuff, so I left that part out. These are pre-installed on my test beds. But once that's there, it becomes actually configuring it. Oh, there you go, my apt-get. That's how you get it for Ubuntu here, this drbd8 utils. And now what we're going to do is there's this file we need to create that actually will configure how drbd will work. In this case, I think I already have it. Yeah. So this is basically just kind of like a template of which node is which. So you'll notice I've got my high availability node 1 and node 2, my .10.20 like I mentioned before. And the syncer rate part is just a default I like to put in there for handy-dandy purposes, because the default I think is SHA1 or some other default that's a little bit slower. I mean, it's mostly just so it can, the checksum it uses when it's actually syncing data, when it verifies each block is the same on each node. So the faster checksum is generally the one you want to use. And then we have our disk SDB, right? It's like chopped off the bottom of my screen. All right, so the other thing we're going to do, and this is true about Ubuntu, and it's probably true about Red Hat also, although the commands are different. And with Ubuntu, it's, I forgot the command, check service or something. But you need to basically tell it so that we don't want drbd to start when the machine boots. Pacemaker will do that for us. If it starts when the machine boots, it could be in a, it could be in a different state. It could try to steal the device from Pacemaker, which we definitely don't want. So we're just going to tell drbd not to start because we hate it. That's for Pacemaker to do. All right. So next thing we do is we actually create the drbd stuff. And really, there's just, really at this point it's just cut and paste. I mean, I can't really explain these. You create the device and then you turn it on. So that's create and up. Where's the freaking, oh, that's irritating. Oh well. Hey, look. We now have drbd devices. Handy. Now, what I'm going to do is I'm actually going to set it up so that node 1 is going to be the primary in all these cases. So that way I know that when I'm doing my experiments, my cut and paste work. Node 1 is going to be our primary. So what this command actually does, this command is actually much easier in drbd 8.4. 8.3 is kind of crufty syntax. And actually, I wanted to mention that because if you actually go and look at the drbd site, they default to the 8.4 syntax. And they say, like, if you're using 8.3, which currently everything does unless you actually physically install 8.4 on your own, you actually have to go to a separate set of documents, and it could get kind of confusing if you use the wrong ones. That one you do on the primary. there we go. Bear with me here, sorry. All right, so it's running on both nodes, it's set up. And one of the things you can see here is it doesn't know which node's primary. It says they're both secondary, they're both there. ProcDRBD is a very handy thing, so it always tells you what is currently going on. The proc file system is awesome. So back to our command that we were going to say the primary. Obviously, I left the command out of here. You have to actually start the DRBD service. I'm an idiot. So, okay, only do this on node 1. We want a primary node. Okay, so what I just did is I'm following this sync process. It's initializing and syncing that to the other node. So basically it's saying all the data on node 2 is bullcrap. I'm just going to replace it all with a synchronization, and now it's done. So now we have a primary and a secondary, and they're both up to date. That's what those statuses mean. And if you're playing with DRBD, the interesting thing is the first node, the node you're on, is always the first element there. So if I go to node 2, notice it says secondary primary. Because they're on node 2, the first thing is the node you're on, and the second one is the remote node. That's probably an important thing to know. All right, so what do we do next? There's a lot of these options in this default file here. They're basically just all the different settings you can turn on and off. Well, some of these are very relevant to your life. So disk barriers, they're write barriers. Some file systems have them, some systems don't. But what it basically boils down to, along with our disk flushes here, is there's certain integrity things that the file system says it will do. And DRBD knows they're there. And if some of these things aren't, honored, then you're not going to get your data written properly. And you can turn these off if you have a battery-backed cache, because it will actually protect your data for you. It'll make sure that the barriers are in place. It'll make sure that the data is written in proper order. But the thing you should never, ever turn off, ever, and I'm not even sure why this is an option, is disk drain. That's something that if you really are an expert, you might be able to play with, but really don't. That's something that should never be disabled, because what disk drain does is it says, okay, I'm giving you the data in this order. Write it in this order. Because it basically drains it, like a LIFO. But, sorry, like a FIFO. So the problem is if you turn that off, it can present the data in any order, and the actual operating system itself or the file system itself can decide to write it in different orders. So you'll end up getting writes out of order, and that will corrupt your data instantly. Really not sure why that's even there. There's probably something I'm just not seeing that is above my pay grade, but again, don't do it. You might be tempted to get some kind of performance boost out of it, but it's just not worth it. So the next thing we're going to do is set up LVM. It sits on top of DRBD because it actually will tell us when DRBD is available. It'll protect it, give us the ability to create snapshots, all the handy things LVM does. LVM actually stands for Linux Volume Manager. If you don't know what that is, I strongly suggest looking it up and reading all about it. It's very awesome. If you ever wanted to get sand level snapshots of your data so it changes underneath you and you can still get a stable data extract of it. That's what LVM does. It can let you change your volumes while they're live. You can add disks to them and make them grow. It's not completely all that awesome, but it does have the ability to kind of do the things you really need to do with your volumes without getting too crazy. So I'm going to go ahead and create a volume, a physical volume. And LVM, this is PV create, physical volume create. I'm telling it the DRBD, the thing that I just created, is I want to watch and monitor it. You only do this on the primary node, thankfully, because this stuff actually will carry over with the file system. It's written into the file system itself. The other thing I'm going to do is I'm going to create a volume group. Now, a volume group can be split up into multiple volumes. And you can actually have multiple physical volumes in a volume group. So I could have like 5 disks in a volume group and then create one giant volume out of them or 100 smaller volumes. It's a really good way to kind of control, abstract your actual volumes away. So I'm creating a volume group, just underscore PG, out of the DRBD physical volume I just created, successfully created. And then the last thing I'm going to do is I'm going to create a 450 meg actual logical volume. Now, remember when I said it was actually 500? Well, I'm saving 50, for stuff. Anything you don't allocate can be used to create more volumes, or you can use it for snapshots, which is handy if you want to say that size is actually, what will happen is when you create a snapshot, data that gets written to your disk, instead of being written to the actual spot where you are, gets written to the snapshot. So you can actually read from the snapshot and get the data before it had changed. It does it in the background. The snapshot you actually mount is the unchanging data, but it writes it in the background so that it's actually your data. It's kind of convoluted, but the thing is, however big the snapshot is how much data your data can change while the snapshot's mounted. So obviously, the longer it's mounted, the more changes accrue, and if that reaches the maximum size of your snapshot, what will happen is the snapshot will deallocate, and you'll lose your snapshot. So theoretically, anyway, you don't lose any data, but we all know that doesn't always happen in practice. So what do we do next? Well, we've got our volume, and it's ready. We just got to put it there. For this particular sample, I'm going to go ahead and use XFS. Now, my friend Greg over here wanted me to mention that XFS, if you're on a Red Hat system, is apparently an expensive add-on option. I didn't realize that. I was just using it because it's handy and it's what we use, and we don't have Red Hat as a vendor, so we don't really get charged by them. But apparently, if you have a support contract with them, that's the expensive way to go. But I'm still going to use it in this example, just because. So you want a place to mount it, obviously. So, PG data. And if you're going to do stuff with XFS, you're going to need XFS progs. Those are the format, MKFS, those things that actually create the file system. You're going to need that. So again, on the primary file system, I'm going to go ahead and format. Boom, file system. And now I'm going to mount it. Now you'll notice my options here. My AG count, that's handy if you have a system with lots of CPUs, because with XFS, each CPU can actually write to the file system in parallel. Well, to each allocation group that's available. Unlike, say, ext3, which only has one allocation group for the entire file system because it only has one file table, XFS can have as many file tables as you want. I just override the default to show you that you can. And again, on our primary file system, we're going to mount this. Oop, didn't get the whole command. All right, so we're mounted, right? Right here, 450 megs. And then I want Postgres to own the mounted version because it's Postgres' data. Isn't that happy? All right, so now that we have, that should already be changed. Nope. Sorry, this tilted podium is really irritating. All right, so next thing we're going to do is we're going to start Postgres to, kind of prove that the data is going to be on both nodes and it's going to sync across both of them. I'm going to mention a couple caveats about Ubuntu here. So when you do get the actual install, you're going to want Postgres 9.1 and the contribs. The contribs are actually where pgbench is stored. So for this particular purpose, that's why I need that. The other thing that I've already done is when you install the Postgres stuff, it creates a default config that it calls main. Well, we want to make a new one that actually points to a different data directory, because the main data directory actually points to like var lib Postgres, something that we, clearly it's not dbp2 data. So we're going to go ahead and, I already dropped this. And the other thing we're going to do on both systems, and I'm going to say why in a minute, is actually create the new HAPG configuration group. You can ignore that. All right, so this is on node 2. And what I'm going to do on node 2, because the only reason I did this is because now I have a config file that's the same on both nodes. I'm cheating here. Right? I didn't care about that stuff. I just wanted the config file. So I've got the same config on each server now. And again, just like I did with DRBD, I don't want the system to manage it itself. This is Pacemaker's territory here. Step on toes here. Again, Postgres is ignored. Postgres is ignored. And here's the, I guess, the coup de grace. We're going to start Postgres. Oh, looks like I got a typo. All right, running, hooray. So the other thing I'm going to do here, and you'll excuse my horrible overuse of SU here, I'm going to create a pgbench database. I'm going to initialize it with a simple, it's only 500 megs, right? I can't really use all that room up. pgbench will help us kind of make some fake data that will be on both servers. Just to initialize it with a set of 5. Yeah, we're creating data. Okay, now we're to the really fun part. So all of that was just to get the stuff up and running. And now we have Postgres on one node. It's ready to switch over to the other node when we actually want to flip over. Pacemaker is the hard part. All that was just preparation talk. So the parts that you're really going to want to watch for, and this is true with both Red Hat and Ubuntu and any Debian or Red Hat-based system, is CoroSync and Pacemaker are the 2 bits that make this work. CoroSync is kind of like the transmission glue. It's basically the interface layer that works over UDP that says, okay, cluster, cloud, these are the configs you're all going to use. If you join the cloud, these are the configs you should connect with. Here's the services you should have running. Here's the things I'm going to check you for. It basically is the management layer between everything. So you're going to want those. Before I forget, I did this before, and it's stupid. Obviously, I can't listen to .30 if I'm listening to localhost only. All right. And I'm going to want to do that in node 2. All right. So that config is ready for when it flips over. I already reloaded it. All right. Whoops. All right, so we're restarted then. Good, thanks for pointing that out. Sorry about that. The other thing we need to do is actually configure CoroSync. Again, this is a file that needs to be on both servers. And the part that actually really matters, this is a big file full of gobbledygook. For the purposes of this, you can ignore most of it. The part that really matters here is the bind net address. Remember how I mentioned I was setting up a VirtualBox? I also set up a VirtualBox network, and it gave me 192.168.56 dot whatever. That's what my network's on. Well, it takes the network mask into consideration, and what it does is it sets up a multicast also on this port. So basically, anything with this configuration that joins the cloud with the UDP traffic for this configuration will show up automatically in the cluster. The other thing I'm going to do is the actual CoroSync default file, it tells it when to start up. That's set to no right now, because obviously we just installed it, and the default for the service is not to start because it's a pretty complicated service, and it needs to be properly configured or it doesn't do anything, right? So I've got a handy sed command that will change that for us from no to yes, because I want it to start now. Magic. Right? Start yes. And I'm actually going to start it now on both servers. Okay, on node 2, I'm going to start a service call, a monitor called CRM_mon. It's a little handy utility, kind of like top, that basically monitors the state of the cluster and says, okay, what do I have in the cluster? What's there? What can I use? And it always shows the current state. So now I've got 2 nodes online that it found, because remember CoroSync, they both have the same network configuration. They both kind of latched onto the same thing. If I added a 3rd node with the same configuration, it would also show up in this list of online nodes. Get this part ready. All right, now we're going to get to the nitty-gritty parts that I kind of hate discussing. So first of all, there's some defaults you need to set up for Pacemaker so that it doesn't get wonky. So Pacemaker is a enterprise-level tool. It really wants to manage your stuff and make sure it doesn't break. So there's a thing called STONIF, which stands for Shoot the Other Node in the Head. Funny acronym, but what it actually means is when it decides that a node is down, it, by default, will do whatever it can to make that node unavailable permanently. And that can include shutting the power off, because there's network interfaces you can actually connect to, and there's services you can actually configure it for to disconnect the network, shut it down permanently, go over a network interface to actually disconnect an entire switchboard. There's actually services to do any of this stuff. And basically what that means is if you have a really big giant cluster, you don't want other nodes to pop up unannounced and start screwing with things until you've gotten to them to make sure they're not, because they were turned off for a reason, right? You don't want them to come back up and start screwing things up. So, but with our 2-node system, we don't care. It's also a VM, so we still don't care. And setting up a STONIF is actually pretty hard. That's one of the things that when you're setting up a Pacemaker, it's just more trouble than it's worth for right now, for this particular demonstration. So if you ever set this up, read up on it, get a Unix admin that knows his stuff, because it's going to be kind of crazy. we're going to turn it off. We only need to do this once because the configuration gets distributed to all nodes, right? It doesn't show up in here because, whatever, but I can do this. And it shows my config. So I got still enabled false, right? The other thing I'm going to do is quorum policy. What quorum policy means is if you're a fan of Evangelion, we had Melchior, Balthazar, the supercomputers that was actually controlling the entire nerve center of the system. Well, they get to vote on what they do, and each machine gets a vote. Well, when a two-node system is around, a vote doesn't mean anything, does it? Right? Because each node will vote for itself. So we're going to go ahead and turn off quorum policy because it's pretty much meaningless. So what I did there is I shut that off, and we'll see here we've got no quorum policy ignore. So basically, the cluster will still operate even though there's no quorum. Basically, you'll need to do this to any cluster you set up that has less than half nodes available, and you still want it to work. The other thing we're going to do, and this is the part that you could miss because you don't really, the thing is, Pacemaker is meant to be transient. You can basically configure it to move services over, so you have you want Apache running and you want, PHP on certain nodes. It can actually move those around where it seems convenient at that time, based on the score involved. Well, we definitely don't want that to happen with Postgres, and we definitely don't want that to happen with DRBD. So we're just going to set a stickiness. At a very low level, we're basically saying, if a service is running on a node, leave it alone. If another node comes up that you think is a better match, who cares? We'll move it later. We'll move it over there if we really want it to be there. Those things really need to be set if you have a two-node system, right? If you don't, what'll happen is if everything is on node 2, and node 1 comes up, which is the default, so remember I set up everything up on node 1. Pacemaker knew that. It goes, oh, you set up everything on node 1, you want it there. I'll shut down Postgres and move it over to node 1 now, since you brought it back up again. No, I don't want that at all. So this is our default, and that's the one we want to keep. All right, so now we're going to start actually managing our services. And just like we built the stack from the bottom up, we're going to set up DRBD, LVM, file system, Postgres, in that order. And this is actually just going to be a fun barrage of cut and paste, but I'm going to kind of explain what I'm actually doing. So the part here, these little bits and pieces, what you actually have when you set up Pacemaker, you have various levels of item. So a primitive is actually the thing you want to monitor and control. It's basically the root core of what Pacemaker is going to do. In the case of DRBD, there's a supplied thing by the vendors, the coders who basically make DRBD that say, okay, Linbit is a company that basically just makes DRBD. They've provided this handy-dandy binary or script set of stuff that manages it for us. So we're going to tell Pacemaker to use that to manage it. All these timeouts are just defaults. I mean, they're here. I'm basically setting it up so that it monitors it every 15 seconds. If it starts, it waits a couple minutes to let it sync if it needs to, yada, yada. These are all defaults. You can actually see, by the way, CRM stands for Cluster Resource Manager. It lets you do pretty much everything. That's all the stuff you can do with Cluster Resource Manager. Whatever. But within those classes, there's things available you can do. So we're just going to go ahead and use the DRBD primitive for the one we created earlier. And again, we only have to do it on the primary node, or actually any node, because it'll just absorb it. So now what we've got is a bunch of errors. That's expected, it's fine. So I added the DRBD device, but the thing is the monitor doesn't know what to do because DRBD actually is not like a regular service. It doesn't run on one node or the other, it runs on both. It's just in a different status on each node. So the other thing I need to do is I've got here this MS here. I'm going to configure a master-slave resource, which basically says, okay, this isn't a regular thing where you just have running on one server or another. It actually has to be promoted or demoted or whatever based on the actual statuses. So this will actually make it work properly. Maybe. Let me make this a little bigger. Because it's going to get pretty darn big. All right, so now notice how it says master slave, and it knows the node node 1 is the master, node 2 is the slave. I'm going to go ahead and clean up these errors because they're irritating. I'll go, wait a minute. All right, so next, we've got our file system. Remember how we have LVM on top of DRBD? Well, we basically have to tell it to scan for the volume group because that's actually where all the data lives. And then down here, we're telling it how to mount it. So we've got, again, we got some primitives for the LVM device and the actual file system itself, type XFS, our different mount options, and some defaults.
Hey, Shaun.
Yeah.
We actually are starting the lightning talks in about 5 minutes.
Okay. Well, I'll just go through the rest of this then real quick.
Okay.
Apparently, I wish I had more time. So I'm just going to go ahead and create the rest of this and do a quick demonstration of what it can do. My slides are actually going to be on the wiki just like the rest of the stuff. What I'm doing now is I'm setting up the Postgres resource monitor, the VIP to monitor the actual IP address we gave it. I'm creating a group that basically ties everything together because I want the volume manager, the file system, and everything else to kind of be in the same thing. And then I want DRBD to follow Postgres wherever we put it. So I won't be able to do all my demonstrations, unfortunately. So I'm going to go ahead and do a failover. And watch this guy over here. Whoops. See what that just did? Now it's running on node 2. And I can prove this because here's node 2. And it says it's primary. And it's mounted. Okay? I'm just going to cut this short. I actually had some other demonstrations where I actually killed my VM and it automatically migrated it. And I brought the VM back and it didn't migrate it over like this prove the stickiness worked. This is all, again, in the liner notes. I really wish I had 2 hours about this, and darn it, I just explained too much of the stuff, tried to kind of explain why I was doing stuff so I wasn't just a cut and paste fiesta. But what you're basically left with is this. And I'll skip through these. And at the end of the note, at the end of the liner notes again, is all the little bits. All these little pieces of documentation are all what goes into this. Like the LSB init script is the most important thing because if you don't have something that's Linux standard base compliant, Pacemaker will not have the right exit codes because you have to say exit with status level 3 if you're shutting down a service and it succeeds, things like that. If you don't have an LSB compliant script, it won't work. So I guess that's it for me. But